Welcome everybody to our discussion of types of bonds. Today we're going to talk about covalent bonds, both nonpolar and polar. We're going to talk about intermolecular forces, ionic bonding, as well as metallic bonds. And we'll rush through all of those real quickly. Let's get started. There's a lot to do. So covalent bonding. Covalent bonds are characterized by a sharing of electrons, and this occurs when the electronegativities of atoms are relatively similar. So when both atoms are pulling on electrons with a similar force, one of the atoms can't overpower and take the electron completely. They end up sharing the electron between the two atoms. And that sharing can be either nonpolar, which means the electronegativities are extremely close together. They're almost identical. And that results in a really even share of electrons. So each atom has it for roughly 50% of the time. There is no charge imbalance there. So no separation of charges. The other possibility is the electronegativities are a little farther apart from each other. So if they're not nearly identical, what will happen is the more electronegative atom will then pull the electrons more strongly, and they'll actually have them around them more often than the other atom. So what you'll find is that atom with more electronegativity will actually have a slight negative charge on it, and the one with less electronegativity have a slight positive charge on it. Is as if it's kind of like a pseudo-ish ionic bond, but it's called a polar covalent bond. So it creates one part of the bond that's positive, the other part is negative. All right, so let's take a look at a nonpolar covalent bond. And an easy way to get a nonpolar bond is just to bond two atoms of the identical element. So like H2 or Cl2 or O2 or N2, all of those are good examples of nonpolar covalent bonds. They have a perfectly even share of electrons. And even a good rule of thumb is if you're more than one square away or tile away on the periodic table, definitely that's going to be a polar covalent bond. And even sometimes when you're within one square of the atom you're bonding with, you still end up being a covalent bond. But the key thing to note here is that anything that's not two identical atoms is going to have some polarity, although it might be really small. So we look at two hydrogen atoms bonding together. I'm going to draw a hydrogen nucleus here and here, so one proton each, and they have one electron around them. I'm going to show those electrons as its electron density. So each of these dots represents where the electron could be at some time. And you'll notice what I'm doing here is I'm drawing the density of the dots close to the nucleus, really dense, and less dense the farther out you get. So if we were to take a picture of a hydrogen atom, like a billion pictures, snapping where the electron is, you'd find it around the center of the nucleus a whole bunch, and the farther away you got, the less likely you would be to see it, so you would see it less often there. So it's good to note here that each of these dots is not an electron. It shows you a density of where the electron is most of the time. So I'll do the same thing on this atom. I'll put a density close to the nucleus, relatively dense. The electron spends most of its time there. And then the farther out, it'll just be, a little less dense like this. And those are two hydrogen atoms, and they're far apart. Okay? So neither feel any forces from the other. I'm going to use this weird word called feel, not like an emotional feeling, but like a pull or a push is a feel. And things that are inanimate can respond to a force, and in this case, that's the word feel mean. Neither feel any forces from the other. So we've gotten them far apart, far enough apart, I should say, so that they're not pulling or tugging on each other at all. But over time, let's say these two atoms do start coming closer together. They do start feeling a force. So I'm going to pull those protons a little bit closer together. And what we find is when they start getting a little bit closer together, these electrons are mobile, and they'll start feeling a pull from this proton. So these electrons will get pulled in this direction. So they'll kind of shift their density from all around to just towards this other one. So I'm going to draw that in here. See how that density is just shifting in this way a little bit? Now they still go on the other side of the atom sometimes. That's not, but it's just less likely. And there's like a little more density here. And this is the same way. It builds up its density. Again, these electrons are being pulled in that direction towards that side. Now at this point they're feeling a force. I made that a little, that shouldn't be so lopsided up there, but they're feeling a force here that's pulling them this way. Well, that means if the electrons are feeling a force pulling them this way, they must be pulling the nucleus that way. So if we draw it, I'm going to switch the color here to blue. If we draw the force, so here's a small force. This nucleus is actually being tugged this way by these electrons. So there's a small force here and a small force here, and this is the force that this nucleus feels being attracted to these electrons. So the blue arrow is the force the nucleus feels from the, sorry, it's a little delay here, the other atom's electrons, right? So this being pulled towards this cloud of electrons, this being pulled towards that cloud of electron. Very cool. Now wait, that's not the only force acting on them though. There's another force that you may have seen here that is a repelling force. I'll do that one in green color. And right now these nuclei are far apart, and there's actually a really tiny repelling force, like that. Right? And this color arrow indicates a repulsive force between nuclei. Right, so here's my electrons are repelling, or sorry, the protons are repelling each other, but they're also being pulled towards electrons on the inside of here. Awesome. Now let's draw the next step. So as they get closer and closer, they're going to, pointer option, we'll switch back over to red real quick. So now we have our protons that have gotten really close together now. And this is getting a little bit hard to draw. And that electron density, this is where the electron clouds start overlapping. And what you end up with is what ends up looking like one big electron cloud, but there's extra density in between them. You see, I'm putting extra dots in between them. Now here's the really, really cool thing. So let me switch over to blue color real quick here. So because these protons are closer to all these extra electrons, the force here is really big, pulling it in this way. And this force has gotten a lot bigger as well, pulling in this way. Again, both these protons are being pulled inward, are attracted to these electrons that are between them. So they're being pulled in here. But of course, that's not the only force going on. If I switch over to a green ink color here, you can see that because they've gotten closer together to each other, there's also a bigger repulsive force. And they'll reach a length, a distance apart from each other, where this green and blue are balanced. And when we hit that, that's what we call our bond length. So this is at bond length. And that happens when repulsive and attractive forces are equal. You get this stable situation where you have an outward repelling of the protons against each other equal to the inward pull of the protons on the electron cloud. Now what if we were to push them a little closer together? So I'm gonna zoom over here for that model and say, so like maybe another hydrogen atom, a molecule came in and bashed this one and pushed it in closer. So you would get these protons that are really close together, closer than they normally would. Well, one thing that would happen first of all is the electrons would get closer together as well, and they would tend to repel each other out of that bond. So our electron density in between may actually decrease. But the really key thing here is that these protons now are way too close together. So what you end up with is an enormous increase in that repulsive force. So it goes whoosh like this. I mean, these like get really big. And when that happens, they get bashed together. As they come together, they push each other harder and harder apart. They slow down and then repel outward from each other. So you get this idea that the bond isn't something like rigid and it's like a stick or a piece of wood that holds them in place right here. It's just being attractive. They get bounced. They're going to bounce too close together and then push apart. But then they get into a situation like this where the inward pull is bigger than the outward push, and they get pulled back together again and then pushed out, pulled back in, and they sit and they vibrate and oscillate. And that's why they vibrate and oscillate, because it's a constant battle between the inward pull and the outward push. Now, the average of that battle is what we call the bond length. I'm going to switch over to black here. So this distance here, when these forces are balanced, we call the bond length. The bond is never actually that length. It's an average around that. So they're vibrating around that length, bigger and smaller constantly. So let's label these pictures. Let's label that one A, this one B, this one C, this one D. And we're going to draw a potential energy diagram. So here we have our chemical potential energy on this axis, and we have our separation, so distance between nuclei on this one. So these are nuclei that are far apart. And on this part of the graph here, they are close together. So right in here, they would be like 0 distance apart, so they would be overlapping each other, which is obviously impossible. And when we draw this, the energy diagram of this reaction, this is what it ends up looking like. So when we start far away, and I'm going to draw this one as like a purple color. As we start far away, we start with some amount of chemical potential energy, or it can be defined actually as 0. It doesn't really matter what the number is. It's just what happens after. So does it get more or less is basically all we're focused on. So as they get closer together, we have less and less chemical potential energy. So because they're coming together, they used to be far apart, now they're coming together, that's converting chemical potential energy. So they have less and less chemical potential energy. Just like as a ball were to fall off a roof and fall towards the earth, as it fell down, it would have less gravitational potential energy as it came closer. These guys have less chemical potential energy. Well, they reach a point here, and this is a weird point. This is where the gravity analogy breaks down, because you adjust as you fell towards the center of the earth, just keep lowering your chemical potential energy because gravity only pulls. Whereas in an atom, there's a pull and a push. Whenever the pull is greater, you're going to be decreasing your chemical potential energy. Boom. Going down to a minimum energy. And that happens right here. So what happens then when we get too close? Well, then the repulsion gets bigger and it actually spikes your chemical potential energy. And it shoots up like this. Now in our drawings here, this part over here is A. We're so far apart, they really don't make any difference. Here, where they're coming together, but they still have more coming together to do, is B. So here, the inward pull of the protons on the electrons, that inward pull is more than a repulsion. And then right here is their minimum energy state, C, and that's their bond length. Now, if we squeeze them together anymore, they become more repulsive and their chemical potential energy actually goes up. And so all over and through here is letter D. So A, B, C, and D. So bond forms, gets too close. So the bond will actually, the length of the bond will stay, in this range. So it'll go whoop, too close, whoop, too far away, too close, too far away, and it'll get pulled and pushed back and forth as it vibrates and oscillates. Now, as the temperature goes up, it's interesting, they'll hit each other harder and cause a bigger vibration, and that makes the bond weaker and makes it more able to break. It's why adding a match to methane makes it go boom. It's just making them bounce more so the bond can break and form new bonds easier. All right, now that was a lot on that. I hope that helps. And all bonds form this way, although this is a very simplistic model. All bonds form in this way of this competing, pushing, and pulling between the two things. Great. Now, polar covalent bonds, these occur when the electrons are unevenly shared between atoms. And this is when the electronegativities are somewhat different. We talked about this before. When they're not nearly identical, they're off by a little bit more, you get this. And what you end up with, and we can look at a really popular one of hydrogen and oxygen and water. So if we have oxygen here, we have hydrogen here, hydrogen here. Hydrogen's electronegativity is significantly less than oxygen's. So the electrons in this bond are going to get unevenly shared around here. Now if we draw this, there's one way of representing it is this. Of course, the simplest way is to draw H2O, right? So that's the simplest way we show water in its formula. We can show it this way, but maybe even a better way is to show it as, a nucleus here for oxygen, and a nucleus, one proton here, and there's this buzz of electrons. And when this bond gets formed, there's a buzz of electrons, and in between the water and hydrogen, or sorry, the oxygen and hydrogen, is this increased density of electrons. And what we find when the electronegativity of oxygen is higher than hydrogen, those electrons get pulled around the oxygen more than they do the hydrogen. So the electrons spend more time around oxygen than hydrogen. So that gives oxygen, and it's not like all the time, so it's not a full charge. It gives it a partial negative. And the way we do that is we draw this little O with a curly Q on top of it, just like, let me erase that and try that one again. I can make it smooth. So we go whoop, 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 whoop. And that's a sigma, and we do that, hey, partial negative. It's a nuisance to draw that thing. And all that indicates is it's not a full negative charge, it's a partial negative. And we put that over here on the oxygen side, and then we go over here and we do the same thing, but we do a positive here and a positive here, knowing that whatever negative we have here is split between these two positives, right? So whatever value that is. So we get a slight positive side of the molecule and a slight negative side of the molecule, and that's a polar bond. Now, the more different the electronegativities are, the larger the separation of charge. So the more different, I'm going to do En for electronegativity. The electronegativity, the greater the difference in charge. And you might see this coming, but we're going to take this to the extreme and say, hey, if they're super duper polar, it's as if the electron's been totally transferred, and we're going to call that a new type of bond, ionic. So really an ionic bond is like a souped up polar covalent bond, where the electron, instead of being shared, have been totally transferred. Here they're unevenly shared, so it's like a spectrum. All right, so that's our polar covalent. Let me erase all this writing so you can see what's there. So molecules with a polar bond may be polar or nonpolar. So just because a bond is polar in a molecule doesn't mean the overall molecule is going to be polar. We'll look at that, what that means. And molecules that have that are polar, that have this distinct positive negative end, they're called dipolar molecules, and they have what's called a dipole moment, and we'll talk about those next. And the more electronegative atom takes on a partial negative charge, the less electronegative takes on a positive charge. I got a little ahead of myself with the drawings, so that's what we just talked about, that one's partially negative, one's partially positive. All right, so now we're going to look at some electrostatic potential maps. And what this is, it's a way to visualize the distribution of electrons. So in one of these maps, and we'll look at it in a second, we use color to show where the charge is negative and where it's positive. Let's take a look, first of all, though, at hydrogen chloride. So as a gas, this is called hydrogen chloride. When it's dissolved in water, it's called hydrochloric acid. That's not important for you to know that. Don't sweat that too much. But so HCl, hydrogen is way less electronegative than chlorine is. So what we get here is we get a pull of electrons that shifts the charge, that shifts electrons this way, making this one slightly negative and this side slightly positive. And we can show that in multiple ways. One is to show the dipole moment, which basically what you do is you do a plus sign with an arrow pointing towards the negative, which way the electrons are being pulled. In this case, plus with a negative. The length of this arrow can indicate how strong that pull is, but it doesn't have to. Here we're just going to show there's a plus here, so it's positive on this end, negative on this end. So that's one way of showing a polar bond. Another way of demonstrating it is with an electrostatic potential map. Now obviously these are much harder to draw, but here the blue are show positive charge, and this orange and red are negative. So it shows you where the distribution of charge is. You can see there's a lot of negative charge here on the chlorine side and a lot of positive here on the hydrogen side. You may be asking yourself, well gosh, why is this important if it's polar or nonpolar? And one of the big reasons is this will tell us if this bond is very stable or not. So a highly polar bond is likely to be easier to break than a nonpolar bond. But also, more importantly maybe, is that these things are going to be sticky for each other. So you can imagine if another HCl was around here, the positive end would be attracted to this negative end, and they would tend to like glom together and stick a little bit. So, and this could be drawn here too. I mean, you could add the dipole moment this way as well, but you can see it more clearly with the color there. Now, if we look at water, and we did water already, so we know that, hey, water, hydrogen is less electronegative, oxygen is more. And if you're asking yourself, hey, how do I know what the electronegativities are? That's why we learn those trends on the periodic table. So if you look, hydrogen's way on the left, oxygen's way on the right, large difference in electronegativities. We end up here with a distribution of charge here. The way of showing that, of course, is to do a plus sign here with an arrow pointing this way, and a plus sign here with the arrow pointing this way. So in this case, we're asking ourselves, well, does the overall molecule have a dipole moment? And the answer is yes, because this bond pulls electrons down and to the right. This one pulls up and to the right. And you notice the down here and the up here uphill. The down from this pull will cancel with the up from this pull, leaving just two pulls to the right. So the overall dipole moment for this molecule is straight this way. It'll go from having a positive end on this side to having a negative end on this side. And we can visualize that again with the electropotential map. And we can see here this side becomes positive and this side is negative. And of course these are only partials. I should put a partial here every time. Partial and partial positive, partial negative. Looks like an 8. So that's 3 ways of showing that. So you can show it with the individual bonds, you can show it as an overall dipole moment, and you can also show it as an electrostatic potential map. Let's look at one more. So we have ammonia here. And well, one last thing, on this one you might be thinking, hey, why is it bent like this? Why aren't the hydrogens straight across from each other? And I'll remind you that the Lewis dot structure for water looks something like this. And the reason it's not straight across is because there's these 2 pairs of non-bonding electrons. They're like here, here, and here, and here. And they tend to force these bonds from being straight across. They repel them, and they end up being bent here by, like say 104, 105 degrees of an angle here. And that's why they're not straight. A similar thing happened with ammonia, so NH3. So we have nitrogen, right? And then there's a hydrogen on this side. It shares an electron. Hydrogen shares an electron. Hydrogen shares an electron. You might think, hey, that should be nice and flat around the middle. But right up here is this region where these 2 unshared electrons, and that presses these hydrogens down a little bit. So it keeps them from being flat and planar. So what ends up happening is there's a dipole moment that pulls up a little bit into the inside. This one pulls up in this way, and this one pulls up in that way. And all the inward pulls cancel out, but because they're all angled up a little bit, you end up with this leftover small upward dipole moment. So you do have a polar molecule here. So NH3, you can see down here is a plus, up here is a minus, and you can see from the colors that this isn't a very big positive partial charge here. It's not blue, it's that teal color, and this maybe didn't really achieve the kinds of reds that maybe water does. So it's less polar than a water, but it's still a polar molecule. They'll still stick to each other, tend to. All right. Now look at some quick examples of some molecules with polar bonds, but that end up being nonpolar overall. And here are two examples. This molecule here is flat and planar. So if you looked at it from the side, these are all in line with each other and on a flat plane going around. So their dipole moments as it goes from oxygen is more electronegative than sulfur, so the plus starts here and goes out, plus starts here and goes out, and then the plus starts here and goes out. And all three of these tend to cancel out, so the outside edge of the atom doesn't have a strong positive part and a strong negative part. It's all pretty similar all the way throughout, so this is non-polar. The only time you get a polar molecule is when these three, or these dipole moments of the individual bonds all point in a similar way, like either up or down or left or right, so that they can add up and create an overall dipole moment. When they're perfectly symmetrical like this, like flat around a plane and evenly spaced, you get something that's nonpolar. Another great example is this one. So this is a methane molecule, CH4, and the dipole moment goes, hydrogen is less electronegative, so it points in this way. There's another one that points up into this way, and another one here that points in this way, and another one here that points in that way. Now, while all of these bonds are polar, they're all pointing symmetrically into the middle. They end up all canceling themselves out, and you don't get regions where it's like really negative here and really positive on this side. You get this even distribution, and this is also a nonpolar molecule. So polarity needs two things. First, you need a polar bond, and secondly, you need those bonds to point in sort of consistent direction, so there's an actual leftover net effect of it. All right. So now these two molecules don't stick together very well. So methane is a gas because it doesn't glom together into chunks and fall to the bottom, and it's in a non-polar, so it doesn't stick well. So that brings us on to our discussion of intermolecular forces. And these are the forces that actually hold molecules to each other, to other molecules, not the atoms inside them. And they're collectively called intermolecular forces. There's a couple different kinds, and we'll delineate those later. You are familiar already, though, with one such force called hydrogen bonding. And hydrogen bonding is an example of an intermolecular force. It occurs... Oops. Hydrogen bonding occurs between two water molecules. So if we have an oxygen, hydrogen, hydrogen, these are a slight positive, these are slight positive, slight negative. The next water molecule will actually, this positive of the hydrogen will be attracted to this negative. And this between these two is what's called a hydrogen bond. So there's an attraction the positive hydrogen and the negative oxygen atoms. And this results from differences or from a polar bond, polar molecule. So a molecule with a dipole. So here, this next one, this little positive here, a little bit negative here, right? So that next water is going to be like here somewhere. Now remind yourself that these things are moving around like crazy fast, but wherever the positives are close to a negative, they're going to stick together and they're going to tend to glom onto each other, and these are all called hydrogen bonds. Now they're not very strong because they're positive and negative. So these are not very strong because they're only partial charges. They're not full charges. And notice the separation here. So these are a good distance apart. So they're not getting that really intimate overlap of their electron clouds and sharing electrons really closely and getting attracted closely. They're still pretty far apart. So it's just a little attraction, a little tug there. And it's why when you drop water onto the table, it forms a little glob instead of spreading out, because they are pulled together pretty well. Our last type of, or second last type of bonding is ionic bonding. And ionic bonding are what we were talking about earlier, just like super extreme polar covalent bonds. So it's when the electronegativities are really different, you get ionic bonds. And it forms so that the electrons, instead of being shared, are basically just transferred from the less electronegative atom to the more electronegative atom. So you get these cations and these anions. So you get a positive cation, negative anion. So if we just do a quick Lewis dot structure of this. So let's say we have a sodium atom with one valence electron, chlorine with 1, 2, 3, 4, 5, 6, 7 electrons. There's such a big difference in electronegativity here. This electron gets plucked off and gets put on, chlorine grabs it. So you end up, when it's all said and done, with a sodium +1 charge and a chlorine atom with a -1 charge. Now, what forms the bond? So when this happens, just the fact that this is positive and this is negative, they're just going to attract each other. It's kind of like a hydrogen bond we just talked about. Except instead of being a partial negative, partial positive, it's a full positive, full negative. So it's strong compared to that. Now, when the next sodium and chloride do this, right, and they form this bond, so when the next sodium chloride form, they're going to actually glom on to these first two sodium chlorides, except the chlorine is going to get pulled towards the positive and repelled from the other negative, so it's going to glom on like right here, negative. And the sodium is going to glom on here, away from its positive and close to a negative, and maybe the next one forms here and the chlorine gloms on there, and the next maybe the next chlorine atom goes here, and the next sodium goes here, and then the next chlorine goes here, and the next sodium finds its way on here, and then maybe there's a chlorine that goes here, and then a sodium that comes on here, and then a chlorine here, and a chlorine here, and a sodium here. And the idea is that we keep building up this crystal, this glom together set of atoms, and we call this a crystalline structure. Whoops. And the result is this interlocking positive, negative attraction between all these different sodiums and chlorides. So it's just the fact that the positive attract negatives, that's the whole bond. There isn't anything, there's nothing, a density of electron in between them, there's no big changes there. It's just this idea of positive and negative interacting with each other and pulling. Now the important thing to note here is, unlike water, there isn't a special bond between two Na and Cl. So for example, I don't even know which one was our first NaCl, but let's say these two were, there's no special bond here. This sodium will attract this chlorine as strong as this chlorine, as strong as this chlorine, as strong as this chlorine. And that's true for all of them. So if you have enough energy to break one of these bonds, you can break all of them. Yeah? So this is a really cool idea that there isn't a particular like NaCl and then next to it's another NaCl. It's just a bunch of sodiums glommed onto a bunch of chlorines in this thing we call a crystal lattice. And they'll keep forming this crystal bigger and bigger and bigger and bigger and bigger. All right. That's ionic bonding. Last we're going to do is metallic bonding. And this one will be fairly quick. We won't spend a lot of time on it. Let's take a look. So metallic bonds form between atoms of a metal. It's why they're called metallic bonding. And something interesting happens when we do this. Since metals have a low electronegativity, they have a relatively weak hold on their valence electrons, which means those electrons can bounce easily from atom to atom. And they form this loose kind of sea, flowing sea of valence electrons surrounding all these positive chunk sort of cations of the metal without valence electrons, and they're all attracted to that sea, and they're all being pulled together by that. So it's kind of like a covalent bond, and they end up having properties that are kind of ionic-ish and kind of covalent-ish. And let's look at what that means. So if we draw an aluminum atom, we have 2 electrons here in the first energy level, and 8 here in the second. And there's no real reason to draw in the electrons here. I'm doing it for example of 1 so we can just see them, right? And we still have 3 more electrons in the third energy level. Before I draw those, let's add a bunch more atoms in. So this would be like a long wire, like filled with atoms, right? So there's a wire that goes through here, and there's a bunch of aluminum atoms in it. Well, what we find is these last 3 electrons in each of these atoms aren't held very strongly. So these 3 electrons actually can migrate in between the atoms, and they can just flow right in through here and through here, and these 3 can go through here and here, and it's like they don't really belong to any atom. They just kind of bounce along in between them, moving freely as if it's just one big electron cloud out here with these little positive insides to it, just zipping along through here, and they can get through. So it ends up being this delocalized like sea of electrons all around each atom. And that's the reason that when you do something strange, like you push an electron on here, like you hook it up to a battery and you push an electron on here, well, an electron can really easily pop off here, because it's all basically just like one big sea of electrons all around these positive cations, these nuclei with those 2 energy levels. So electrons can just flow on and flow off, no problems. Whereas if you try to do that with water, it'd have to jump onto a water molecule, bump into another molecule, get bounced onto that molecule, and on and on and on until it was transferred around. Whereas here, it's like once you push it on here, they just all flow and shift down, and one pops out. So it's a really cool idea here of how electrons are able to be, shared across multiple atoms. And it's all because those valence electrons are held weakly by the atoms. So something else that's cool about this is it's one of the reasons that metals are so easy to be able to bend and flex and hammer out flat. Because if I were to jam this part of the atom and push it down, it'd have no problem with that, because it's always surrounded by this sea of negative electrons. It'll never be repelled. It'll still always be attracted, even if you shift it over some or this way some. Whereas if we look at a quick little crystal of sodium chloride, a little crystal of sodium chloride here, and so we have a chlorine minus here and an Na plus here. If we were to hit this with a hammer, it would shift it over so that the chlorine and chlorine would line up, and this sodium and sodium would line up. So it would shift them over, and then they would repel each other, and they wouldn't stay stuck together. They would crumble into small chunks, and that's why ionic things like salts, right, are brittle. If you hammer on them, they tend to break, because as you shift those ions over, they repel each other instead of attract. And metals aren't, because as you shift this over, there's still this sea of electron around all of them, kind of holding them together still. Now, the reason they're kind of covalent-ish is what holds them together is this nucleus is pulled towards this sea of electrons all around it. And this one is pulled towards these. So they're all being pulled inward by the sea of electrons. And you get this nice, strong, relatively strong bond called a metallic bond. All right, Awesome. Oh, one last thing on this metallic bond, actually, before we move on, is that notice that it's not like water, where it was like an H2O and a separate H2O, right? And there was like space in between them. Each of these, like an ionic compound, each of these is being attracted to each of the other ones equally. There isn't a preference and a grouping up of stuff. They're all just one big glom of stuff. And that's another thing that gives metals its cool properties. All right, awesome. That ends our discussion of bonds. I hope it was helpful.